Hello, 171 class. This is your notes for section 1.3. First thing in this section is increasing, decreasing intervals for functions. So if a function is increasing on an open interval, that means this fancy mathematical definition, this is like the lower y coordinate, like the first y coordinate you come to is less than the second y coordinate you come to when x1 is less than x2, which basically means as you move left to right, the function's going up, higher and higher. Okay, and decreasing then would mean as you move left to right from x1 to x2, the function's getting lower and lower and lower. Okay, and then constant would mean as you move left to right, we're not going up or down. Okay, we're staying the exact same height. So, easy way to remember it. This is where we're increasing because it's going uphill as I move from left to right. This is the way it's where it's decreasing because it's moving downhill as I go left to right. And then this is where it's constant because it's not going up or down as I move left to right. So if you just think of it as uphill, downhill, constant. So decreasing, increasing, and constant. So you can also picture someone walking, okay, but they'd have to be, again, it's all about moving left to right, so it'd have to be, facing this way. So as they're walking left to right, if it's a decreasing interval, they're going downhill. If it's an increasing interval, they're walking uphill. And if it's a constant interval, then again, the elevation's not changing. You think of it that way. Okay. So that's the easy way to remember. It's just think about the motion, the direction has to be left to right, and then it just becomes is the graph moving down, moving up, or staying level. All right, so the way we write these are in intervals. So if I'm looking at this first graph, where is it increasing? Well, it's increasing from here to here. Okay, it goes up. Okay, and it's always x coordinates. For what x values is the graph going uphill? So that's the way we answer it. So it starts at excuse me, 0, and it stops at 2. All right, and this is just like domain and range. When we write these, we write it with an interval notation. So it's going from 0 to 2. It's increasing in that interval. The graph's getting higher and higher and higher as we make our way from 0 to 2 for x. But we don't ever put the endpoints in these, meaning we always use parentheses. So 0 to 2, this thing's going uphill. Now where is it going downhill? Well, if you look, it's going downhill. Again, thinking about moving left to right, I'm coming downhill for this whole entire little piece right here, but that's got an arrow on the end. So remember, it means it keeps going up and up and up and up forever. So this thing is going downhill, even though it's out of the screen, for all the way back to negative infinity. And then from right there at the 2, it starts to go downhill again, and we get an arrow. So that means it's going to go downhill all the way through to positive infinity. So the way we write that, because there's more than one interval where it's decreasing, if I'm thinking about this little green chunk right here, where does it start? Well, it starts at negative infinity. Where does it stop? It stops at 0, where it starts turning to go back uphill. So negative infinity to 0. And then we put this little u because there's another section where it goes downhill. All right, that u is called the union. And then we start another parentheses, and then right here this other green section is where it's decreasing. So that starts at 2 and it goes to positive infinity. Alright, for constant intervals, there is no place on this graph where it turns constant like this. Okay, so there isn't nothing, so we can just, there is a symbol, this is like a 0 with a line through it, which means no solution typically is what you've probably seen it as before, but it also means an empty set, meaning there is no place where this graph is constant. There isn't an interval. The graph goes constant. Alright, here, increasing. This thing is increasing from the point 0, 0 all the way through. So it's increasing from 0 to infinity. Alright, it's never decreasing. There's never a place where as we're moving left to right, the graph is going downhill, so we can have the empty set symbol there. Or you can just write none. And then where is it constant? Again, this arrow keeps going back to the left. So this place where the constant interval starts is negative infinity. And where does it end? It ends at 0. Now this closed dot means that point is included, but it's not included in the constant increasing or decreasing interval because if you go back and look at your definitions for increasing, decreasing, and constant intervals, we always have these strictly greater than, strictly less than symbols. Okay. So we don't include that endpoint for any of these intervals. So just leave it blank. Okay. The problem is, again, for a point to be included in an increasing, decreasing, or constant interval, it has to be doing that on both sides of the point. Meaning, for 0 to be included here, it would have to be constant on the left side of 0, like the negative numbers, and a right side of 0, like a positive number. But it's not constant on the right side. It starts increasing on the right side. So 0 is not included in that constant interval. Alright, relative maxima, relative minima. This is simply like the peaks and the valleys. Alright, a relative minimum is where we change from decreasing to increasing. A relative maximum is where we change from increasing to decreasing. So the way we say this is f of b is the relative maximum, and it's located at b. Okay, f of a is a relative maximum, it's located at a. F of b is a relative minimum, it's located at b. So the x-coordinate is the location of the relative min, relative max. The y-coordinate is that relative min, relative max. Okay, and what we mean by relative is that it's the biggest thing, the biggest value in a region close by. It doesn't have to be the biggest overall. Like, for instance, this particular function, this arrow the graph keeps going. It's indicated by that arrow. This keeps going downhill, as indicated by the arrow. So this point right here, b, f of b, is not the lowest. Okay, there's a point over here that's lower, but there exists an interval, is basically the idea. There exists some interval down here on the x-axis where this is the lowest point. Okay, there exists some interval down here on the x-axis where this is the highest point. Okay, yeah, there is a higher point, but this is the highest point in an interval close by this. So that's what I mean by relative. Relative to the points close by this one, this is the highest. Relative to the points close by this one, this is the lowest. Now, other values, if there is a biggest on an entire interval, or an entire graph, not just an interval, the entire thing, it's called an absolute maximum or minimum. Like, for instance, the graph y equals x squared that just has that look. Right? It decreases and then it hits that low point and then it increases. Well, that's the low point. That's the by definition, it is a relative minimum, but it's also an absolute minimum because there's nothing lower at any point on the graph. All right, let's come over here to this example and make sure we got it. Okay, so on the interval from negative pi to positive pi of this graph. Okay, and this is something that a graph that you'll see in 172 if any of you go on. This is called a sine curve. But if we're looking from negative pi to pi, we're looking on this interval right here. What is the relative minimum and the relative maximum? Or is there a relative minimum, relative maximum? Yes. There's a relative minimum. There's a relative maximum. Now, the relative minimum is -1, right? And it's located at negative pi over 2. Okay, the relative maximum is +1, and it's located at positive pi over 2. All right, so again, it's important for you to get down who is the relative minimum and where is the relative minimum located. Who is the relative maximum and where is the relative maximum located. It's always, if you notice, it's the answer to the question where, these intervals and these points, is always an x coordinate. Where is the relative maximum? It's at A, and its value is f of A. Where is the function increasing? It's increasing on this interval of x values. Okay, where is the function constant? It's constant on this interval of x values. So where is always x's, and what in this case is the y. What is the relative minimum? It's -1. All right, where is it? It's located at negative pi over 2. Okay, so where is x and what is it is y. All right, even and odd functions. A function's even if when I plug in negative x into the function, I'd get the same thing out as if I plugged in positive x. And if it's odd, then if I plug in negative x, then I get the opposite of when I plug in positive x. So let's look and see what we mean by that. So for A here, if I plug in negative x, I cube the input and I subtract 6 times the input. So I cube the input here is negative x, and then I subtract 6 times the input of negative x. Alright, cubing -3 means literally negative x times negative x. And then -6 times negative x is positive 6x. Alright, and then negative times a negative times a negative is negative. X times x times x is x cubed plus 6x. Now if you look, I could pull this negative out here. There's a leading negative. If I pull it out, I end up with a negative and then a parentheses x cubed, a positive 6x. If I pull a negative out, I end up with a minus 6x. And if you look, if I distribute that negative back through, I get negative x cubed. Negative times a negative is a positive 6x. Now, these two things are the same. But if you look, this x cubed minus 6x is what I originally started off with. That is f of x. So this is f of x right here, but there's a negative out in front of it. So this is the opposite of f of x. So f of negative x equals negative f of x. F of negative x equals negative f of x. So that means this is an odd function. Alright, for B, I plug in negative x into the g function. Okay, this is f up here, but it's fine to do it for g and h. It's just the name of the function. This is negative x to the 4th minus 2 times negative x squared. Well, just like I did here, I'd have a whole bunch of negative x's multiplied together 4 times. Alright, and then minus 2, and then another negative x multiplied by itself. So negative times a negative times a negative times a negative, a whole bunch of, an even number of negatives makes a positive, and then this is x to the 1, 2, 3, 4. Alright, and then a negative times a negative times a negative is a negative, and then 2 times x is 2x squared. And if you look, x to the fourth minus 2x squared minus 2x squared, this is g of x. So g of negative x is equal to g of x. F of negative x equals f of x. It's an even function, so this is even. All right, and then finally h of negative x. So I'm going to square negative x. I'm going to multiply negative x times 2 and then add 1. Alright, negative x squared is negative x times negative x. Positive 2 times negative x is minus 2x plus 1. And then negative times a negative is a positive. X times x is x squared. And if you look, we keep the sign for x squared. We keep the sign for plus 1. But we change the sign for 2x. So this is not h of x. And it's not negative h of x either. Because if it was negative h of x, then all three signs would be opposites. Only the 2x is opposite. This is not a minus x squared and a minus 1. So it's not even because it's not equal to h of x. It's not odd because it's not equal to negative h of x. So this is neither. Neither even nor odd. Okay, so that happens a lot. Now if you look, odd degree on the exponent or odd exponent, odd function. Even exponent, even function. Okay. 2 is an even number, 1 is an odd number. We've got a combination of evens and odds. That's a neither. Okay, that's the easy way to know this. Now, for the purposes of using that little shortcut, constants are considered evens. Okay, so if this had been x cubed minus 6x plus, 2, then we would have, even if it was plus 1, we'd have odds for the 3 and the 1 here. Okay, it's understood 1 as that power, both odd numbers, but then the constant would have been even, and it would have been neither. Okay, so it has to be all odd exponents to be an odd function, all even exponents to be an even function. All right, any combination of evens and odds will give you a neither. All right, even functions are symmetric by the y-axis. So what negative x, f of negative x equals f of x means is the y-coordinate when x's are opposites is the same. So the y-coordinate here is 5 when the x's are opposites, 3 and negative 3. The y-coordinate is 0 when the x's are opposites, 2 and negative 2. The y-coordinate negative 3 is the same when the x's are opposites. The y-coordinate is the same when x is opposite in general. So that's what we mean by, visually, that's what it looks like. F of negative x equals f of x. Alright, now, odd functions have something called y-axis, or origin symmetry. So f of negative x equals the opposite of f of x means if you give me an x, 2, you give me the opposite, negative 2, the y values will be opposite also. And so what happens here is we go through the origin and then hit the origin from a point on the graph. And if we go that exact same distance out the other side of the origin, we'll hit another point on the graph where the x's and y's are both opposite of what they were on the other point. So positive x, positive y, negative x, negative y. Now if you look back at this original one we did, this example we did for relative min and max, this actually has odd symmetry also. It's got that origin symmetry. Negative or positive pi over 2, positive 1, negative pi over 2, negative 1. Okay, it has that same origin symmetry to it. So just know that that's what we mean by origin symmetry. Okay, it seems weird to be symmetric by a point because the origin is just a point, but that's what we mean by that, is if we go from a point on the graph through the origin, out the other side the same distance, we'll hit another point on the graph. Alright, another big concept in this section, piecewise functions. A piecewise function is a function where the way you get the output is broken up by where you are in the domain. Okay, so your inputs are produce different outputs at different places. So where you've probably seen or could visualize anyway, a piecewise function is a cell phone plan. So you have a fixed number of minutes that you buy, and then if you go beyond that number, so 60 is how much they bought, if they go beyond 60, they get charged 40 cents per minute. So give me a number times bigger than 60, like for instance 61, right? 61 minus 60 is 1. That's 1 minute over. You get charged 40 cents, right? If it was 65, 65 minus 60 is 5. 5 times 40 is 2. That's $2. You've been charged $2 for going 5 minutes over. 2 plus 20 is 22. So it's $20 a flat fee all the way up to 60. And then anything beyond that, you have to pay this extra 40-cent fee. Okay, so piecewise functions are realistic. They do exist commonly in practice. It's just not all of them are going to be the things that we look at like this. This is not something common in practice. This is something you'd see in a math class. But this is very common to see different pricing plans or cost functions determined by what the input is. And that happens quite often actually. Alright, graphing a piecewise function. So this is telling us to do one thing from 1 or less and to do something else on the other side of that. Now I want to show you how to do this on a calculator. So let me move this over a little bit. I'll bring the calculator in here. So I'm going to put in this 1/2 x squared. Now, to get this to happen, to get the if x is less than 1, go back to the beginning of what you would normally graph. By the way, let's just graph it just to show you this is 1/2 x squared. But if we want to restrict it to only be in the stuff less than 1, here's where 1 is. So we only want to graph to there. Alright, the way to do that is to come back in here. Second delete will insert something. And now you see that cursor is just like underlined down here. I'm going to put a parenthesis at the beginning and end. So this is the thing that I'm wanting to graph. Now, the if part, the way we get that is we do a division, slash, and then parentheses, and now we're going to write this. Alright, x is less than 1. The way we write that is x, just the same way we got the x right here. And then to get the less than symbol, it's underneath the test menu. So second math is test. And then there's your order symbols. And we want less than, so that one's option 5. Less than 1. And then close that off. And now when I hit graph, notice there's that same parabola, but it stops right there. It doesn't go and graph the right hand side of it like it did before. Okay, and then I want to do the other side of the graph, so I'm going to go down to y2. Parentheses 2x minus 1, just like before. Close parentheses. If I'm going to do the divide by parentheses, x is second math greater than or equal to is number 4. 1. Alright, notice now it's going to pick up and start graphing on the right side of this thing. So there's what this thing looks like. So I'm going to put it in your notes. And then what I want you to see here is right there in the middle, not in the middle, but where this thing goes from a parabola to a line, that's that cutoff. That's where x is equal to 1. X is equal to 1 is a vertical line, if you remember from like your high school algebra days. So there's the line x equals 1, and on the left side of that, which this means less than 1, the left side of 1 on the x-axis, you get the parabola. All right, and then there's 1 again on the right side of 1, you get this line, 2x minus 1. Okay, now if you don't put that in there, if you don't put these restrictions in there, what I've done here is I've turned off these two graphs by highlighting the equal sign. You just hit enter and you can turn off a graph. And then I've typed in these two, which are 1/2 x squared, 2x minus 1. It's just the things that I was supposed to graph, but without the restrictions of where I'm going to graph it. And you see that it graphs the entire parabola and graphs the entire line, and you don't get the piecewise graph. Remember, this is no longer a function because there's two outputs for a given input. Okay, you can't have both of them plotted. It's only going to give you one x per each y. It's only going to give you one y for each x. That's what it's supposed to do. Alright, so now I'm going to turn these back on and these back off, and then show you on the table by pressing second graph. See where it says error? Alright, that means it's not graphing the parabola all the way up to that 1. Alright, it is graphing the parabola all the way up to that 1. It's not graphing the line. The y2 is the line. And then beyond 1, from 1 on, it's not graphing the parabola anymore. Now it's only graphing the line. Alright, so it's doing the error part in the region that it's not supposed to graph. Okay, so it's only giving you one y for any given x, and the other part it's giving you an error because it's not supposed to graph there. And then when you switch, right there at 1 is where we made the switch. Now it switches over and it starts graphing in the other region. Okay, so anyway, I wanted you to see that that's how we can graph a piecewise function with your calculator.